Spiral galaxies, characterized by their luminous arms winding around a central bulge, have long captivated astronomers. However, their graceful rotation and structural integrity conceal a profound cosmic mystery: the invisible hand of dark matter. Observations spanning decades reveal that the visible components of spiral galaxies, stars, gas, and dust, account for only a fraction of the gravitational forces governing their motion. The remainder arises from dark matter, a non-luminous substance that permeates galaxies in vast halos, extending far beyond the visible disk. This dark matter not only dictates the rotational dynamics of spiral galaxies, but also influences their formation, stability, and star-forming activity. By examining the interplay between dark matter halos and baryonic matter, we uncover the mechanisms through which this enigmatic substance shapes the morphology and evolution of spiral galaxies. The gravitational influence of dark matter first became evident through the study of galaxy rotation curves. In a spiral galaxy, stars and gas orbit the galactic center with velocities determined by the mass enclosed within their orbital radius. This discrepancy, known as the galaxy rotation problem, suggests that spiral galaxies are embedded within extensive dark matter halos, contributing up to 90% of their total mass. While the spherical assumption simplifies calculations, the true shape of dark matter halos remains uncertain. Observations of flaring layers in edge-on spirals hint at flattened halos, but conclusive measurements require further study. Regardless of their geometry, dark matter halos provide the gravitational scaffolding necessary to maintain the coherence of spiral arms and prevent the dispersal of stars and gas due to centrifugal forces. The relationship between a galaxy's mass and its rotational velocity is codified in the Tully-Fisher relation, which posits for spiral galaxies. This empirical law emerges naturally when dark matter halos dominate the mass budget, as their gravitational potential wells set the maximum rotational velocities attainable by baryonic matter. These superspirals challenge alternative theories like modified Newtonian dynamics, MOND, which cannot reconcile their breakneck spins with the observed baryonic mass. Dark matter also governs the specific angular momentum of galactic disks. The fall relation holds across 4 decades of mass, indicating that dark halos and baryonic disks share self-similar angular momentum distributions. This alignment suggests that dark matter halos acquired their spin during the early universe's tidal torquing, with baryons conserving angular momentum as they collapsed into disks. Such coherence implies a quiescent accretion history for spirals, distinct from the chaotic mergers shaping elliptical galaxies. While dark matter halos enable the existence of extended galactic disks, they also modulate star formation efficiency. Studies comparing spiral and irregular galaxies reveal that spirals exhibit higher star formation rates, lower gas fractions, and shorter timescales for gravitational instability growth. This dichotomy arises from dark matter's role in stabilizing gas disks. In spirals, massive halos suppress large-scale turbulence and confine gas to the disk plane, promoting rapid cloud collapse. Conversely, irregular galaxies, with shallower dark matter potentials, experience delayed star formation due to inefficient cooling and higher centrifugal support. The vertical structure of spiral disks further reflects dark matter's influence. Flaring layers in outer disks indicate reduced gravitational pull from the visible disk, necessitating a dominant dark halo to prevent excessive thickening. Additionally, simulations suggest that dark matter halos absorb angular momentum during galactic mergers, preserving the thin disk structure of spirals over cosmic time. Superspirals, the most massive known disk galaxies, exemplify dark matter's pivotal role. These behemoths rotate at velocities surpassing 500 km/s, sustained by dark matter halos comprising over 95% of their mass. Their existence defies MOND predictions, which fail to explain such velocities without invoking non-Newtonian dynamics. Moreover, superspirals exhibit anomalously low stellar masses relative to their halo masses, suggesting that dark matter regulates baryonic accretion. Two mechanisms may operate: halo gravity shocks infalling gas, heating it beyond cooling thresholds, and rapid halo spin impedes gas collapse via centrifugal barriers. Despite its explanatory power, the dark matter paradigm faces unresolved questions. The core cusp problem, discrepancies between predicted dense halo centers and observed constant density cores, remains contentious. Additionally, the paucity of observed satellite galaxies compared to LCDM predictions hints at incomplete understanding of dark matter microphysics. Alternatives like MOND adjust gravitational laws to eliminate dark matter but struggle with galaxy cluster dynamics and cosmological observations. Meanwhile, emergent gravity theories remain speculative. Thus, dark matter remains the most viable framework, bolstered by cross-correlations between galaxy surveys and gravitational lensing maps. Dark matter halos are the architects of spiral galaxies, sculpting their rotation curves, stabilizing their disks, and modulating their star formation histories. From the subtle flaring of layers to the breakneck spins of superspirals, dark matter's fingerprints permeate every scale of galactic dynamics. While mysteries persist, particularly regarding halo structure and baryonic feedback, the synergy between observational astronomy and cosmological simulations continues to illuminate dark matter's role in shaping the universe's grandest spirals. Future advancements in radio astronomy and dark matter detection experiments promise to unravel remaining enigmas, further cementing dark matter's status as a cornerstone of modern astrophysics.